All right, let's get started. So, hi everybody. Thank you so much for joining this webinar today. So during today's session, we will talk about SK Telecom Sovereign AI Cloud, and we will be sharing some practical insights into the scalable AI infrastructure. Speakers that are joining us today are Dr. Jian Li, who is the Principal Engineer at SK Telecom, as well as Jeffrey Tay, who's Regional Director for AI and CSP for APJ Advanced Data. This is an interactive session, so you're welcome to submit your questions through the Q&A panel that you see on the left-hand side of your screen. We will be covering them during the Q&A segments at the end of the session. So with that, let's get started. I will pass it to Dr. Li.
Okay, so I'm Jian Li, working at SK Telecom, and I'm lead AI infrastructure and the cloud virtualization effort at SK Telecom. And my expertise is in GPU virtualization, AI cloud platform, and edge computing technologies. And in my role, I've been deeply involved in designing our Petasus AI Cloud platform and integrating cutting-edge storage solution. So today, I'm really excited to talk about why we undertook this ambitious project to build a sovereign AI cloud in Korea and how it will impact our industry and the technology community. Okay, so in this slide, I'd like to share the SKT's vision for driving AI innovation. And our strategy rests on the three pillars. One is the AI data center, and another is the AI chipset, and the last one is a multi-LM. So first, we are expanding a global AI data center footprint with the differentiated energy solution and the specialized AI hosting services to meet the growing model and the workload demands. And second, on the hardware side, through Sapion and its merger with Rebellion, we are delivering the next generation silicon like Atom chip to accelerate AI workload more efficiently. And finally, we are also advancing the multi-LLM capability by developing our own A.X LLM while partnering with the leading AI players such as Anthropic and OpenAI to bring best-in-class model and integrations to customers. So together, these efforts position SK Telecom to power scalable and efficient and collaborative AI deployment worldwide. So this slide shares a quick updates on the SK Telecom's new sovereign AI infrastructure and the role our in-house technology played. So SK Telecom has launched the Hein cluster, one of the Korea's largest GPU cluster with over 1,000 NVIDIA Blackwell GPUs, delivering GPU as a service for high-performance AI workloads. So named Hein to symbolize a national AI landmark. So the cluster has been selected to support the Ministry of Science and ICT's proprietary AI Foundation Model Program and will serve as a core resource for national model development. Critically, this deployment leverages SKT's internally developed Petasus AI Cloud solution as the virtualization backbone and enabling us to instantly partition and reconfigure the massive GPU fabric to match customers and the research needs, which maximize the utilization and the agility. Petasus not only maximizes utilization and agility, but also powers our AI ops capability, streamlining the full lifecycle for training and inference. This achievement was realized through close collaboration with the industry partner, including Penguin Solutions, Supermicro, supplied high-performance compute platform and integration expertise, while Vast Data also delivered the high throughput and low latency storage needed for large model training and the data pipelines. This slide shows why we must virtualize AI infrastructure for foundation model work like the world's best LLM, WBL program funded by the Ministry of Science and ICT. because each tenant is developing their own sensitive and independent model, and we need the perfect isolation at both the GPU fabric and the storage fabric level, not just namespace, but isolated HGX, DGX slice that behave like separate physical systems. So virtualizing HGX, DGX server lets us present the secure GPU and the GPU cluster to different teams while keeping the high infrastructure utilization. And critically, when multiple tenants share a single server, we still need the high-speed GPU to GPU communication. And here, NVLink virtualization provides that low latency and the high bandwidth path between the virtualized GPUs, so distributed training and the inference keep near native performance. This slide compares the three ways to partition AI resources. So traditional VM, virtual machine, and the container, and the containerized VM, what we run at SKT with the KubeVirt on top of Kubernetes. So virtual machine gives strong isolation and that each tenant have a guest kernel for specialized GPU drivers, but they are harder to optimize and orchestrate at scale. So containers are lightweight and highly performant under Kubernetes, but they don't provide the level of kernel or hardware level isolation we need for sensitive and tenant-specific foundation model work. So for the WBL program funded by the MSIT, each tenant must see a fully isolated GPU fabric and storage fabric, effectively secure the HGX, DGX slices. So containerized VM combine the best of both. They preserve the kernel level isolation, so we can expose the virtualized HGX, DGX, and the guest driver and the NVLink included, while integrating with the Kubernetes for lifecycle and the scheduling and observability. So that balance security and the multi-tenancy and the cloud data management is why Petasus AI Cloud uses containerized VM. So this slide shows the Petasus AI Cloud architecture. So our Kubernetes-based virtualization platform designed to simplify and accelerate AI workloads, and its core Petasus virtualize the accelerator and the infrastructure so teams can run VMs, containers, or fully manage Kubernetes on a single unified cloud. That means heterogeneous workloads, training jobs, and inference services and the legacy VM tools all coexist and are managed from one platform. Two key strengths to call out. First is multi-vendor accelerator support, and the Petasus virtualizes GPU and NPU across vendors, including the NVIDIA, AMD, and Intel, and Rebellions, and more, and letting you to allocate the hardware acceleration where it's most effective. And the second is heterogeneous workload support. By combining KubeVirt and Kubernetes and the container orchestration, we make it easy to provision, scale, and move AI workload without rewriting them. In this slide, I will briefly explain why DGX, HGX systems are so important for large model work and what we must preserve when virtualizing them. And the DGX, HGX servers are built around SXM-type GPU that don't just sit on a board. They are tightly coupled with the NVLink, a high bandwidth and low latency fabric that GPUs communicate as if they were a single and a massive processor. And that NVLink mass what make fast distributed LLM training and the real-time inference possible. So when we virtualize DGX, we can treat GPU as an isolated PCI device. The virtualization stack must preserve the NVLink topology and the inter-GPU bandwidth through careful device pass-through and the topology-aware scheduling and the virtual GPU technology. So models still see the same near-native communication performance, and the failing to do so breaks the scalability and slowing the training and the inference. Instead of fractionalizing a single GPU, Petasus AI Cloud partitioned the SX Type 8 GPU module into integer sub bundles and enabling instant provision of the multi-vendor GPU cluster while maintaining the secure isolation without the cost of a traditional hypervisor. So crucial, even when a SX8 GPU module is in partitioned GPU within the same sub bundle retain the ultra-low latency and the high bandwidth NVLink connectivity, allowing them to communicate over NVLink as if they were a single monolithic device, preserve the GPU-to-GPU performance for the tightly coupled parallel workloads. So we ran NICO peer-to-peer bandwidth test and high-performance Limpact HPL benchmark on both bare metal H100 HGX nodes and the virtual machine created by the Petasus. By virtualizing NVLink and enabling the GPU direct RDMA GDR, the VM achieved the NVLink level throughputs, and the P2P bandwidth bar for VM NVLink and the bare metal are essentially overlapping, and HPL scores that are virtually identical. So overall, we observed around 1,700% performance improvements over the PCIe, and the overhead introduced by the NVLink virtualization is less than 1%. So in this study, I'm going to briefly explain how Petasus virtualize the GPU fabric to deliver the both high-speed GPU-to-GPU communication and the district tenant isolation. So the challenge is simple. Cloud tenants need the direct low-latency GPU communication for larger AI workload, but we must prevent a cross-tenant data path. And Petasus solved this by virtualizing RDMA fabric, both InfiniBand and Rocky V2, using the partitioning and the GPU direct RDMA. And at the top, a unified fabric manager and the subnet manager program, partition table across the switches and HCAs. So each tenant get the partition key, and you can see the example like 7F and the 80 and the 9F on the same on the slice, and those keys carved the fabric into the isolated slice. And the HCA on the HGX node are bound to those partition entries, and so devices in a different partition cannot talk to each other. And the red X in the diagram shows that district isolation. Then within the partition, we enable the GPU direct RDMA inside the VM, so GPU can perform direct zero copy transfers into the remote GPU memory. That removes the CPU and the system memory from the critical data path, lowering the latency and increase the throughput and reducing the host CPU overhead. So what we are looking at are the NICO over-reduced benchmark run across the multiple HGX H100 nodes, and comparing bare metal to Petasus created virtual machine. And on the left, the throughput and the latency curve for 32 GPU cluster showed VM, the bare metal lines tracking almost perfectly. On the right, we compare the cluster size and the partitioning. Again, the throughput curve with and without partitioning are essentially overlapping. So the takeaway here is straightforward. So fabric virtualization and the partitioning introduce negligible overhead, and whether you virtualize the NVLink fabric or carve GPU into the partition, end-to-end communication bandwidth and as well as the NICO performance remain effectively unchanged. And in practice, this means you can safely and share and isolate accelerators resources in the multi-tenant environments without sacrificing the scalable performance your large model training and this PC workload require. So AI storage on a critical path for training and the inference, so virtualization must avoid added the latency and the throughput loss. So in collaboration with the vast data, we virtualized the NFS-style storage and validated the 3 production-ready configuration, a CSI-based NVMe or TCP path for VM workload, and a virtual function link aggregation, VF flag-based native NFS over TCP, and the VF flag-based native NFS over RDMA. So the VF flag-based native NFS over RDMA option delivers the best result, and it bypasses both the guest and the host kernel IO stack, and yielding the throughputs and the latency comparable to the bare metal. So that said, achieving this requires careful engineering and integrating multipath RDMA column module inside the VM and using the RDMA optimized NFS client and configuring the VF flag for HA and enforcing the advanced virtual NIC behavior, including the EC and the PFC and other league level performance policies. So to remove that kind of operational burden, Petasus automate the entire sequence from RDMA multipath and the NFS client wiring to the VF flag and the virtual NIC tuning. So the operators can attach AI storage to a VM with a single click. So the result is a manageability and the multi-tenancy of the virtualized storage with the near bare metal performance that modern AI workload demand. So we ran FIO performance benchmark on both bare metal H100 HGX node and the virtual machine and created by the Petasus. And by performing end-to-end AI storage utilization optimization, the VM achieved bare metal grade IO throughputs and IOPS. And the VM native NFS over RDMA approach achieved around 600% better performance compared to the CSI-based NVMe over TCP. And the overhead introduced by the AI storage virtualization is less than 3% in this case. So yeah, so this is my last slide. So of course, SK Telecom's Sovereign AI stack didn't appear from thin air. It roots trace back to the early ambition to bring ultra low latency compute at the telco edge. So in 2020, as SKT rolled out one of the world's first national like a scale 5G network, we began experimenting with the mobile edge computing MEC, deploying a very small scale data center inside telco central office to push compute closer to the user traffic. But low latency required a virtualization layer unlike anything on the market. So off-the-shelf software stack from VMware or via OpenStack couldn't provide the tight performance controls or real-time responsiveness SKT requires. So SKT chose to build our own platform, Petasus, engineered to manage the performance and the sensitive jobs at the network edge. So when Korean government announced the World Best LLM initiative, our work on the Petasus suddenly gained a new level of relevance, and that the same problem of network latency and the strict isolation and the instant provisioning that define the edge requirement map nicely to the to GPU-intensive AI workload. So reflecting this evolution and expanded mission, Petasus has been rebranded as Petasus AI Cloud and a sovereign AI cloud platform designed for secure high-performance GPU virtualization at the nation scale. So this is the end of my talk, and thank you for your listening.
Thank you, Dr. Lee, for the insightful presentation. And it is our pleasure to welcome SKT into the world of VAST. I'd like to take a few minutes now to broaden our lens and share some perspectives on how we at VAST partner with some of the largest neoclouds around the world and the Asia-Pacific region. We see this space as very much an ecosystem that is a critical part of our business, with each of our partners pushing the boundaries of scale, sovereignty, and innovation in the regions that they operate in. One thing we learn is that when customers work with VAST to build a sovereign AI offering, sovereignty never has a single definition. Each country and each neocloud provider interprets the notion of sovereign AI in their own way. The unifying theme, however, is consistent. When nations say this is our AI, it means the data is secure, the infrastructure is within in-country boundaries, and the system is accountable to local standards. This means that to help these operators be successful, VAST needs to provide a white glove treatment in multiple aspects, whether it's engineering, product, or business. The way neoclouds approach these functions are drastically different, with each engagement teaching us something new. And in our collaboration with SKT, VAST has gained tremendously, both technically and strategically. On the backdrop of our collaborations with customers like SKT, VAST has continuously aspired to build production-grade innovations beyond storage. This journey has led to the VAST operating system, a collection of data, compute, and agent orchestration functionalities that we recently unveiled to the world, representing our interpretation on how we need to evolve for the agentic era. Today's AI infra is still fragmented and siloed, and it simply wasn't designed to handle the thousands of agents now coming online across enterprises and governments. We see sovereign AI cloud providers already stepping in to try and bridge this gap and are beginning to host more inferencing workloads and agents for their customers. To put it into perspective, projections suggest that organizations may run anywhere from 1,000 to 2,000 AI agents per employee in the future. Our co-founder, Jeff Danworth, recently described this moment as the biggest tech refresh in history. For VAST, this represents a tremendous opportunity to partner with neoclouds to jointly evolve, and we are proud to be on this early journey with SKT, building AIOS functionalities together with them that they can in turn offer to their customers as part of their sovereign AI cloud offerings. A critical part of the AIOS that ties it all together and that I want to spend some time highlighting is what we call the VAST data space. At its core, VAST data space is about helping customers activate their sovereign data and resources no matter where they reside. Whether these assets are in a sovereign cloud, an on-premise environment, or at a hyperscaler, data space brings them together into one unified environment. Beyond infrastructure, data space harmonizes people and talent, enabling distributed teams across locations to collaborate on the same datasets with the same security and compliance guardrails as if they were working within one sovereign system. And that's really the promise of data space and the VAST AIOS, activating data, infrastructure resources, and talent in real time. It's about giving enterprises and governments the confidence to innovate securely, at scale, and in a way that aligns with their sovereignty needs. With that, I'd like to invite Dr. Lee back into the conversation as we shift into a more dialogue-driven format, and we'll also take some questions from the audience. Kicking off the first question to you, Dr. Lee. Earlier, you outlined the challenges and motivation of GPU virtualization and how SKT addressed them by allocating GPUs in multiple blocks to preserve performance. Could you elaborate on this design choice and how these technical optimizations translated into tangible benefits?
Sure, yeah. So actually, the current national program requires a sovereign AI platform that keeps data and models and infrastructure under domestic control and not a rebranded hyperscaler. So that demanded fine-grained multi-tenancy and auditable isolation and the rapid on-demand provisioning rather than a static bare metal like reservations. So by reflecting that kind of requirement, so the key technical optimization what we implemented is RDMA pass-through and the SRV pass. That we eliminated the host guest kernel I/O hops that traditionally choke the GPU I/O. So by routing the I/O via the SRV VF and enabling RDMA pass-through, and we achieved the throughput and the latency essentially is distinguishable from bare metal. So in our case study, our benchmark shows the throughput on par with the 14 gigabyte versus 3.6 gigabyte for the native TCP and the CSI paths, and that was a central win for virtualized GPU performance. And the topology of our GPU partition is another key technology that we have it's enforced in this case. So instead of fractionalizing single GPU, Petasus partitioned the SXM8 GPU modules into integer sub bundles like 2, 4, 6, and 8. And the GPU inside the sub bundle retained the NB-link connectivity. So tightly coupled distributed training keeps the same intra-node performance characteristic as a single physical device. So and this preserves inter-GPU bandwidth and reduces cross-tenant interference. And the hybrid VM container runtime with the scheduler network stealing is another like a key point. And the Petasus expose a unified virtualization layer supporting VMs and containers managed Kubernetes even. So the scheduler is a topology aware and it places GPU allocations to preserve NVLink locality. It uses RDMA for the internal transfers and steals bandwidth to meet the workload needs. And the last but not the least, the storage network level isolation and the VAST days architecture is integrated as a storage fabric and enforces per tenant isolation at the fabric and network level, dedicated network segments and QoS control per tenant IO path. So that reduces the attack like a service compared to the relying purely on the hypervisor isolation and preserve the noise neighbor IO from degrading the other tenants.
That's a real insightful perspective, Dr. Lee. I think we at VAST are aligned to how you set up your infrastructure, and we do agree that keeping GPUs busy really isn't just about how you slice them. It's also about making sure the IO path can keep up in a secure and simple manner. Building on that and moving on to the next round of topic around scalability, I just wanted a bit of your perspective on specifically on a cloud orchestration perspective. What strategies or platforms are you using to dynamically scale GPU and data resources for large-scale AI training and inferencing? I think inferencing was all the rage, in the last 12 to 18 months, but of course now we are seeing a shift towards inferencing demands as well. So how do you balance this resource utilization and also meeting your strict customer SLAs?
Yeah, so those are two questions. So first question might be the how dynamically scaling the work, right? So the integer GPU bundle electricity is one key point. So GPUs are in our case is managed in the integer sub bundle. So for example, like XXM module granularity level. So the orchestration plane can split or assemble bundle across the node and map them into the tenant virtual cluster. So this allows fast horizontal scaling while preserving the NVLink locality where required for the training. And the policy-driven topology-aware scheduler is another key point. So the workloads register requirements, for example, like a strict low latency inference versus the throughput training. The scheduler uses topology and the NVLink maps, RDMA fabric, and the storage QoS to pick the placement that meets those SLA. So for distributed training and the schedule, for the distributed training, the scheduler prefers placements that minimize cross-switch RDMA hubs. So in our case, we mostly consider the not the leaf span type of fabric. So yeah, in our case, it's a little bit different. But anyway, so that's the provisioning path is the last point that I want to emphasize. So thanks to the VM golden image plus the vast data's API-driven provisioning, tenant environments, including the compute and the storage amounts, are ready in minutes rather than days, and enabling the elastic GPU consumption with the low operational friction. And regarding to the balancing utilization versus the SLA, the hard isolation for the critical SLA for customer that will call guaranteed latency or maybe throughput, especially for the inference endpoints backing production services. And then we allocate dedicated virtual cluster with the reserved network and the IO bandwidth and the strict QoS rules on storage fabric. And those clusters are backed by the redundancy and hot standby policies. The elastic pools for the best effort and discounted workload is another thing that I want to emphasize. So for non-critical training job or spot low priority workloads, we place jobs into the oversubscribed elastic pools that can be preempt or maybe thwarted when higher priority SLA demand resource. And this increases overall utilization without demanding detangling the guaranteed SLAs. So the last is instrumentation and SLO enforcement. So the comprehensive telemetry, such as the Prometheus plus integrated VAST metric, feed the real-time SLO checks in the control plane. So if a tenant's performance falls below the threshold, the system ought to remediate it, or maybe by migrating or maybe increasing the QS, spin up additional GPU before a formal SLA alert is fired.
Right. Dr. Lee, I think that really broadens the conversation to the whole AI data pipeline now that your tenants are demanding more stringent and more stable infrastructure. I understand that SKT's AI Cloud integrates with multiple data sources now that your tenants are also demanding you to support multimodal workloads. How have you architected your data ingestion and pre-processing pipelines to minimize bottlenecks, challenges when dealing with these kinds of workloads like video, text, and sensor data?
So I think the key takeaway here is co-designing the data and the compute is really important, and don't treat storage as a passive backend. That is important. So we built a unified data fabric by utilizing the vast dates plus the Petasus compute fabric. So the data flows directly to the GPU with as few copies and hops as possible. That approach eliminates the typical I/O choke point during the multimodal pre-processing and the LLM dataset assembly. So to be specific, concrete pipeline elements and optimization, what we have tried, and the shared everything and the disaggregated storage fabric, which has been mostly provoked by the vast data. So the vast data provides a single namespace that serves object and file and the block access pattern simultaneously. So that video might be frames and transcripts and maybe telemetry land in the same high throughput fabric and be accessed by the different pipelines without staging to the multiple stores. So this reduces the redundant I/O and storage format conversion. And another thing is zero copy RDMA data pass to compute. So by using the RDMA pass-through and the sROV, we create near zero copy pass from the storage fabric into the GPU node. And the large video frames can stream directly into the GPU memory or into the NVMe page accessible to the GPU for decoding and the pre-processing, avoiding the host CPU copy overhead. And the last is the protocol and the format consolidation. And the data fabric supports multiple protocols, including like S3 object and NFS and NVMe. And so ingestion pipeline can pick the best access method per workload without the extra ETL cycles. So Golden VM image auto mount the right data set shares via the vast client. So workloads start with the data already attached.
You spoke about the partnership between SKT and VAST, right? And really describing it as a true co-design and collaboration rather than perhaps a supplier relationship. I think looking back since we engaged, it has been a good, I think 16 to 18 months, if I recall. Looking from your perspective, what were the most pivotal moments in this collaboration so far?
Yeah, I think I want to use this opportunity to show my real appreciation to the vast data, and this project success really hinged on the genuine co-design with our partners like vast data. It wasn't just SKT built X and vast provided Y. It was engineers working together from day one, and that approach was critical because many of the solutions are outside the scope of any single vendor's off-the-shelf product. So for example, creating that NFS over RDMA over VFLAG solution requires both SKT's expertise in cloud orchestration and the VAST's deep storage knowledge. So by co-engineering, we could quickly iterate on problem and find the real fixes rather than patching around the limitations. So the most valuable insight we gain here is from SKT. So from SKT to VAST, we brought real-world production requirements and scale out orchestration knowledge, which helped the VAST team to tune their system for our use cases. And from VAST to SKT perspective, they brought a fresh perspective that we think storage as a software defined and scale out, which really change how we view data orchestration in the cloud.
Thank you, thank you, Dr. Lee. I just want to take this chance to address a question from the audience. It is directed to VAST. So the question was, AI seems to be going to need long-term memory very soon. What kind of changes are expected in the VAST data platform architecture? So I think for us, we do agree, long context, KV cache has become topics that are very prevalent, not only at VAST, but within the industry. I think if you look at basic storage services that we call data store, in time you will start to see VAST supporting and growing development around vectors and time versions objects. So embeddings, documents, and event histories are stored together, snapshot, and they are ideally made to be very queryable in near real time. I think if we look at around the memory governance and lineage area, we have invested and are continuing to invest provenance, audit trails, and cache hygiene, so the agent memory is trustworthy. And eventually, when this memory needs to be audited or explained across tenants or an external auditor, this can be pretty much retrieved very, very seamlessly. And I think on the last point, I touched on it a little bit on the VAST OS short presentation earlier. Through agent engine and inside engine, some of these functionalities that we're building with NVIDIA and design partners, agents ideally will have very simple memory and API or MCP ways of interacting with your own agents and other agents in the future. And this is really the world that we see that we think will play out in some form of capacity in the future. So that's what VAST is doing in that space. I'm just looking through the questions and a check on time. I think we might be heading towards the end of the session. I think we do have one last question, and I think it's an important one to close on. And this is directed to you, Dr. Lee. So I think in your presentation, you talked about how SKT arrived at this juncture, and really about the future in the area of inferencing, agents, and scheduling and orchestration. From your perspective, broad question, where do you see technical and organization breakthroughs will be the most critical for sovereign AI clouds to support this next generation of AI-driven AI?
So maybe this might be some comments or maybe some insight from my side. So for sovereign clouds to host the next generation of agents, I think you need a coordinated breakthrough across the hardware and software and network and storage and organization like design, and not a single magic bullet. So Petasus plus the VAST data co-engineering approach, like a disaggregated storage and RDMA path and push-aware orchestration and the confidentiality control, is exactly this kind of integrated stack that make agent scale and the low latency and the sovereign AI practical. And a bit moreover, for organizational collaboration, for any organization facing maybe like a similar issue like SKT, so large scale virtualization of a specialized hardware with heavy needs. My advice is integrate early and deeply, and don't treat storage and networking as a afterthought. So consider them core parts of your virtualization platform, and also to automate the entire stack so that everything from compute to the storage is provisioned together. So this pays off hugely in operational simplicity and the performance. And finally is remember that I think the collaboration is a really key. So the complex system like this is often involves many technologies, and work with partner who can co-develop and test with you is a key point that I want to emphasize at this session.
Right, and Dr. Lee, from the VAST side, perhaps from a bias perspective, we really see the future of this space being shaped by data agility. We see inferencing and real-time agents demanding smaller and more elastic GPU resources. But we think that they only succeed if the data layer can deliver context instantly and securely. And that's why we've been investing in forward-looking initiatives like the VAST AI OS. And when providers like SKT can scale agents with data in the right place and the right time, we think we are in for a very exciting future. With that, I think we have come towards the end of this short webinar. It's been a pleasure hosting this session with you, Dr. Lee. Thank you for generously sharing your perspective. And with you, there's never enough time to cover everything. And we'll now bring the session to a close. Thanks again to you and our audience for being part of this webinar. Thank you.
Thank you.